You've just unboxed a new iPhone 18 Pro. The weight is perfect, the screen is impossibly bright. You swipe, and the interface glides under your thumb with zero friction. It feels less like a machine and more like an extension of your thoughts. You open a demanding application, edit a high-resolution video, and the device doesn't even stutter. It feels like magic. But what if I told you the most important part of this device, the tiny silicon heart that makes it all possible, wasn't made by Apple? And that the story of how it's made isn't just about technology, but about a secret, multi-billion-dollar handshake that dictates the future of computing for the entire planet. This is the story of the most deeply integrated and financially symbiotic partnership in the modern technology industry. It's not a simple supply agreement between a customer, Apple, and a manufacturer, TSMC. It is a high-stakes financial gamble, a pact we'll call the Wafer deal, where Apple pre-funds TSMC's riskiest technological leaps in exchange for a temporary monopoly on the world's most advanced technology. It's a deal so powerful, it has allowed them to create their own private version of Moore's Law, leaving the rest of the industry perpetually one, very expensive, step behind. For over half a century, the digital revolution was powered by a remarkably simple and reliable observation. In 1965, a young engineer named Gordon Moore, who would later co-found Intel, noticed that the number of transistors that could be squeezed onto a microchip was doubling roughly every 2 years. This wasn't a law of physics, but an observation of progress. And crucially, as the transistors got smaller, they also got faster, more power efficient, and, this is the most important part, cheaper per transistor. Moore's Law was the engine of exponential growth, the predictable rhythm that made today's science fiction tomorrow's consumer electronics. But that engine has started to sputter. The relentless march of miniaturization has run headfirst into the fundamental laws of physics. Transistors, which began as chunky components measured in micrometers in the 1970s, are now being built at the 3-nanometer and even 2-nanometer scale. A human hair is about 80,000 nanometers thick. We are now engineering at the level of just a few dozen atoms. At this scale, the bizarre rules of the quantum realm take over. Electrons, the lifeblood of a circuit, can tunnel through physical barriers they shouldn't be able to cross, causing short circuits and errors. The sheer density of components generates so much heat that it threatens to melt the chip from the inside out. Engineers have devised ingenious solutions, like 3-dimensional FinFET transistors and the next-generation gate-all-around GAA architecture, to keep the scaling alive. But these solutions come at a staggering cost. The cheaper part of Moore's Law is gone. The observation isn't dead, but it has evolved. It is no longer a simple prediction of progress. It has become a brutal economic challenge. To continue shrinking transistors, you need to build some of the most complex and expensive structures on Earth, a modern semiconductor fabrication plant, or fab. The cost of building these facilities is escalating at a terrifying rate. A decade ago, a leading-edge fab might have cost a few $1 billion. Today, a fab capable of producing 3-nanometer chips costs an estimated $20 billion. The next generation, a 2-nanometer fab, is projected to cost a mind-boggling $28 billion for a facility with a monthly capacity of just 50,000 wafers. To put that in perspective, the world's most expensive aircraft carrier, the USS Gerald R. Ford, cost about $13 billion. A single chip factory now costs more than 2 of them. The primary driver of this astronomical price tag is the equipment inside, particularly the machines required for a process called lithography, which is essentially a hyper-advanced form of photography used to etch circuit patterns onto silicon wafers. To create features that are only a few nanometers wide, you need light with an incredibly short wavelength. This is the domain of extreme ultraviolet, or EUV, lithography. The sole supplier of these machines is a single Dutch company, ASML. Each EUV machine is the size of a city bus, contains over 100,000 components, and costs more than $150 million. A new fab requires dozens of them. This capital expenditure, or CapEx, is a new kind of arms race, and it's reflected in the price of the final product. The silicon wafer, a 300mm disc from which hundreds of individual chips are cut, is the fundamental unit of production. As the process nodes shrink, the price per wafer skyrockets. A 7nm wafer from a few years ago cost around $10,000. A 5nm wafer costs about $16,000. A 3nm wafer, the kind used in the latest iPhones, is priced around $20,000. And the next generation 2nm wafer is expected to cost an eye-watering $30,000, a 50% price jump in a single generational leap. This exponential increase in cost has created what can only be described as an economic wall of physics. Historically, the promise of Moore's law was that innovation would lead to better performance at a lower cost per function, making the massive R&D investments economically self-sustaining. That virtuous cycle is now broken. To push past the physical barriers of quantum mechanics, a company must first be able to scale an economic wall of unprecedented height. Committing $28 billion to build a factory for a 2nm technology that has not yet been proven to work at a commercially viable scale is a bet the company risk. Technological leadership is no longer just a function of brilliant engineering. It is a direct function of the ability to fund and de-risk monumental capital expenditure. It has become a global game of financial chicken, and there is only one customer on the planet with the scale, the ambition, and the cash reserves to not just play the game, but to fund the construction of the entire stadium. Faced with this terrifying financial landscape, TSMC, the world's undisputed leader in contract chip manufacturing, needed a partner. Not just a customer, but a co-investor willing to share the burden of pioneering the next frontier. They found that partner in Apple. This relationship is built on a unique and largely secret financial arrangement, the Wafer deal. The core of the deal is Apple's massive multi-billion-dollar prepayments to TSMC, often made years before a new process node is ready for mass production. While other companies wait for a technology to be proven, Apple steps in at the earliest, riskiest stage. It effectively books the entire initial production capacity of a new, unproven technology. It did this for the 3nm node, securing 100% of the initial supply for its A17 Pro and M3 family of chips, giving it an exclusive window of access for roughly a year. And it's doing it again for the upcoming 2nm node, reportedly securing nearly half or more of the initial capacity for its future A20 and M5 chips, long before competitors can even get in line. But reserving capacity is only half the story. The truly revolutionary part of the deal lies in how the risk of failure is managed. Manufacturing semiconductors at the atomic scale is an unforgiving process. When a foundry like TSMC pioneers a new node, the initial yield, the percentage of functional chips on each wafer, can be frustratingly low. Reports suggest that for the 3nm process in its first year, yields were around 70%. This means for every 10 chips produced, 3 were expensive, useless slivers of silicon. In a typical foundry relationship, the customer pays for the entire wafer, defects and all. The cost of those failed chips is simply part of the price of being on the cutting edge. But Apple, thanks to its immense scale and financial leverage, has negotiated what industry insiders call a sweetheart deal. Under this widely reported arrangement, Apple only pays for the known good dies, the chips that actually pass TSMC's rigorous quality control tests. To understand the significance of this, imagine you're ordering 100 custom-built engines for a new line of supercars, knowing that the factory's new process means 30 of them will be flawed and unusable. Normally, you'd have to pay the cost for all 100 engines. But Apple has a deal where they only pay for the 70 perfect ones, and the factory has to absorb the cost of the 30 failures. Now imagine each engine costs not thousands, but hundreds of thousands of dollars. That's the scale of the financial risk that TSMC is absorbing on Apple's behalf. This arrangement effectively saves Apple billions of dollars on each new generation of chips. This structure is more profound than just a clever procurement strategy. It represents a fundamental shift in how the financial risk of technological innovation is managed. A new process node is, at its core, a high-risk R&D project. The initial phase is defined by trial, error, and a high rate of failure. The sweetheart clause contractually transfers the direct, multi-billion-dollar cost of this learning curve from Apple to TSMC. Apple provides the massive, upfront capital that makes the entire R&D endeavor possible, but it has simultaneously engineered a unique risk transfer mechanism that insulates it from the direct financial consequences of TSMC's inevitable early struggles. Apple gets all the upside of being the first to a revolutionary new technology, without bearing the direct financial downside of the messy, expensive process of its creation. It is an unprecedented arrangement in high-volume manufacturing, turning a simple customer-supplier dynamic into a deeply intertwined financial partnership. This unique financial arrangement creates a powerful, self-reinforcing cycle, a win-win engine that has propelled both companies to the apex of their respective industries. For TSMC, the benefits are existential. Apple's guaranteed prepayments provide the predictable, massive cash flow needed to de-risk the monumental capital expenditure of building a new fab. It gives them the financial certainty to break ground on a $28 billion facility years before they have a single, commercially viable 2-nanometer chip to sell. This guaranteed demand from their largest and most reliable customer allows them to plan capacity with confidence, ramp up production, and perfect the manufacturing process at a scale no other company could provide. For Apple, the reward is a clear and defensible technological monopoly. For a critical window of 6 to 12 months, Apple is the only company on Earth that can build products with the world's most advanced silicon. This isn't a minor lead that can be closed with clever software or marketing. It is a fundamental, generational advantage in physics and engineering that resets every single year with the launch of a new iPhone. The tangible results of this advantage are on full display every autumn. When Apple launches a new flagship iPhone, it's not just introducing a new device, it's showcasing the real-world output of the Wafer deal. Consider the launch of the iPhone 15 Pro, powered by the A17 Pro chip. It was the world's first smartphone built on TSMC's 3-nanometer process. Its direct competitor, Qualcomm's Snapdragon 8 Gen 3, found in flagship Android phones from Samsung and others, is a powerful chip, but it's built on TSMC's older, less advanced 4-nanometer process. While benchmarks for multi-core performance can be competitive, the A17 Pro's more advanced node gives it a fundamental advantage in the metric that matters most for mobile devices: performance per watt. Because its transistors are smaller and more efficient, the A17 Pro can perform the same amount of work while consuming less power. This translates directly into a superior user experience. In single-core tasks, which affect the perceived speed and responsiveness of everyday actions like opening apps and scrolling, the A17 Pro holds a convincing lead of over 25% in benchmarks like Geekbench 6. But the real story is battery life. In head-to-head tests, an iPhone 15 Pro Max, despite having a physically smaller battery, can outlast a Snapdragon 8 Gen 3 powered competitor by over an hour under heavy use. This isn't just about a bigger battery, it's about a fundamentally more efficient engine. If the iPhone's annual leap is the consistent drumbeat of this partnership, then the transition of the entire Mac lineup from Intel processors to Apple's own M-series chips was the symphony. This audacious move, which stunned the PC industry, was the ultimate validation of the Apple-TSMC strategy. It was only possible because of the immense scale and deep integration forged through the iPhone partnership. Apple had the confidence to design a revolutionary family of desktop and laptop-class chips because it knew TSMC had the world's most advanced manufacturing technology. funded by a decade of iPhone sales, ready to build them at scale. The results were transformative. The very first M1 chip, built on TSMC's 5-nanometer process, delivered performance that rivaled high-end Intel chips while consuming a fraction of the power. This created a new generation of MacBooks that were not only faster, but also silent, fanless, and had all-day battery life, a combination previously thought impossible in high-performance computing. The cadence of improvement has continued, with each new M-series generation leveraging a new TSMC process node. The M3, for example, built on the 3-nanometer process, delivered a roughly 30% multi-core performance gain over the M1, a direct result of the move to a more advanced node in just a few years. This predictable annual performance leap in Apple products is not a natural market phenomenon. It is a privately funded, exclusive, and manufactured reality. Moore's law used to be an observation of an industry-wide tide that lifted all boats. The Wafer deal has changed that. It creates an exclusive year-long window where only Apple has access to the cutting edge. This means competitors are structurally, not just competitively, a full generation behind. Qualcomm isn't using an inferior 4-nanometer design by choice. They're using it because the entire 3-nanometer capacity was already booked by Apple. This cycle repeats every year, creating a manufactured performance gap. It's no longer a law of physics, it's a law of economics and supply chain control. The Apple-TSMC alliance now dictates the pace of innovation for the entire high-end consumer electronics industry. They have effectively privatized the cutting edge, creating a new proprietary rhythm of progress that we can call the Apple-TSMC law. To understand the power dynamics of this relationship, one must grasp the sheer scale of Apple's financial contribution to TSMC. In 2022, Apple's orders constituted 23% of TSMC's entire $72 billion revenue. In 2024, with TSMC's revenue surging to over $90 billion, Apple's share is estimated to be over 22%, translating to more than $19.4 billion in spending. No other single company comes close. Apple is not just a customer, it is the financial bedrock upon which TSMC's technological leadership is built. This deep trust was forged out of a strategic business model. TSMC's legendary founder, Morris Chang, pioneered the pure-play foundry model. Unlike an integrated device manufacturer, IDM like Samsung or Intel, which designs its own chips and manufactures them for others, a pure-play foundry only manufactures. It never competes with its customers. This was a critical factor in winning Apple's business away from Samsung, which is not only a component supplier, but also Apple's fiercest rival in the global smartphone market. Apple needed a partner it could trust with its most valuable intellectual property, and TSMC's model provided that assurance. This symbiotic relationship, however, raises a critical question about power. While TSMC has a roster of other world-class customers, NVIDIA, AMD, Qualcomm, and Broadcom all rely on its manufacturing. None command the sheer volume or possess the willingness to pay the massive premium for the absolute bleeding edge like Apple does. This has led some analysts to describe TSMC's position as a golden cage. The cage is gilded with tens of billions in guaranteed annual revenue, but it's a cage nonetheless. Apple's immense leverage gives it an outsized influence over TSMC's corporate strategy. The decision to build a massive multi-fab campus in Arizona, for example, was heavily driven by geopolitical pressure from the US government and the explicit commitment from Apple to be the site's first and largest customer. Apple's product roadmap dictates TSMC's technology roadmap. In its official investor communications, TSMC emphasizes its broad customer base and diversification as a key part of its risk management strategy. But this public messaging belies the structural reality of its deep dependence on a single customer for its most advanced and profitable technologies. In truth, Apple's role has transcended that of a mere customer. It now functions as the anchor tenant for the entire global technology ecosystem. When TSMC decides to build a new $28 billion fab, it's Apple's massive guaranteed order that provides the financial foundation to make that project viable. This initial high-volume production run for the newest iPhone allows TSMC to work through the difficult and expensive teething problems of a new process node, refining the manufacturing process and dramatically improving yields over the first year. After Apple's exclusivity period ends, TSMC can then offer this now mature, higher yield and de-risked process to its other customers like Nvidia and AMD. These companies gain access to world-class technology without having to fund its risky and expensive infancy. In essence, Apple pays a pioneer tax to be first, and in doing so, it subsidizes and accelerates technological access for the rest of the high-performance computing industry a year later. The Wafer deal is the economic catalyst that pulls the entire industry forward, with Apple firmly in the driver's seat. For all its success, this trillion-dollar partnership is built on a geopolitical and technological fault line. The concentration of power and production creates a series of profound risks that threaten not just the two companies, but the entire global economy. The single greatest risk is geography. Over 90% of the world's most advanced semiconductors, the chips smaller than 10 nanometers, are manufactured in one place: Taiwan. This small island exists in a state of perpetual tension with its much larger neighbor, China, which considers Taiwan a breakaway province and has not ruled out the use of force to achieve unification. A military conflict or even a blockade of Taiwan would be catastrophic. It would instantly halt the production of nearly all advanced electronics, from iPhones and AI servers to critical military and medical equipment. The global economic fallout is estimated to be in the trillions of dollars, a shock that would dwarf any previous supply chain crisis. In response to this clear and present danger, a global effort to diversify the semiconductor supply chain is underway, spearheaded by the US CHIPS and Science Act. The most visible result of this is TSMC's massive new campus in Phoenix, Arizona, an investment that will eventually exceed $65 billion. This project, heavily subsidized by the US government and anchored by Apple's commitment, is a crucial first step. However, it is a hedge, not a solution. The Arizona fabs will remain a generation behind Taiwan's leading edge for years. The costs of manufacturing in the US are significantly higher, and even at full capacity, they will represent only a small fraction of TSMC's total global output. It would take an estimated $350 billion and several years to build enough capacity outside of Taiwan to replace its output. The current diversification efforts are, therefore, less about creating a truly redundant supply chain in the short term, and more about strategic signaling and political appeasement. It shows a commitment from the US to onshore critical technology and gives companies like Apple a made-in-America story to tell. But the real, unspoken contingency plan is far more dramatic. It has been reported that both ASML and TSMC have a poison pill, the ability to remotely disable the critical EUV machines in the event of an invasion, rendering the multi-billion-dollar fabs instantly useless to an aggressor. This threat of mutually assured economic destruction serves as a far more powerful and immediate deterrent to conflict than a fledgling factory in the Arizona desert.